Okay, so now we're getting into a new section. Should check for chalk first. So focusing on orthonormal expansions of functions, and now we're going to focus on a particular kind of orthonormal basis. And these are solutions of Sturm-Liouville problems, so which are eigenfunctions. So the properties of Sturm-Liouville eigenfunctions and eigenvalues. Okay. So after dealing with general Hilbert spaces for a while, we're coming back to differential equations. So looking at a general Sturm-Liouville problem that arises naturally from separation of variables applied to various PDE. PDEs in one space dimension. Okay. And this is the ODE. So we have some Sturm-Liouville operator, L of B, and I'm going to use a slightly different sign convention that we'll see at various points in the book, where they have this differential operator, P of x u prime plus q of x times u, and I'm going to take all of that and put a minus in front. And then this is set equal to lambda r of x u. So I'm putting a minus over here. The book tends to put it over here. Because I want to have, on the right side, nothing more than an eigenvalue, wave function, and then your solution u. So this right here is a Sturm-Liouville operator. And this will make other equations later on more convenient to use this convention. All right. And this is enforced on some interval AB. Now, there are two kinds of Sturm-Liouville problems that we're going to discuss. In many cases, the same properties apply to both, but not always. In terms of boundary conditions. So for a regular Sturm-Liouville problem, you have these boundary conditions, a boundary operator that involves both the solution value and its derivative value at the points A, B. And
was it equal to or minus?
Sorry, what?
BAB minus BB.
No, so this is an equals.
Okay.
So they're both equals 0. Okay. And just to refresh your definitions, each of these boundary operators is a linear combination of the function values and derivative values at that point. Okay, so both these are equal to 0. So this accounts for special cases, Dirichlet conditions, Neumann conditions, and then in a general case, Robin boundary conditions. Okay, so that is, so you put the two together, this ODE in these boundary conditions, that's called a regular Sturm-Liouville problem. And then we also have periodic Sturm-Liouville problem. And that just means that the function values at the endpoints are equal, and the derivative values at the endpoints are equal. Okay. So I'll be talking throughout mentioning its properties, regular Sturm-Liouville problem or a periodic one. Okay. All right. So we have like a zillion properties to go through, and I actually don't. I'm going to prove many of them. I don't expect to get through all of them today. In fact, bless you. In fact, I prefer not to, just because I had to write more notes sooner. So, in fact, I guess I hindered myself by starting on time. Okay. All right. Well,
Take a break.
nah, that's okay. Well, I guess educational research says you're supposed to, but yeah. Okay. So first we have a proposition about when you have solutions of this ODE, that the solutions themselves don't necessarily satisfy the boundary conditions, do you actually have an eigenvalue of the Sturm-Liouville problem? Because as we've seen in examples, there are infinitely many solutions of this ODE for different values of lambda. Now, this is second order ODE. So if I fix lambda, you can have at most two linearly independent solutions. But if we allow lambda to vary, we have uncountably infinitely many solutions, because each value of lambda gives rise to its own solutions. But only certain one of those, only certain values of lambda actually lead to solutions that also satisfy your regular boundary conditions or your periodic boundary conditions. And those give rise to the eigenvalues and eigenfunctions. So the first thing we're going to look at is, if you have solutions of the ODE for a certain value of lambda, do you actually have an eigenvalue, and are those solutions actually eigenfunctions? And it turns out it's very easy to determine whether that's the case. Yeah, so on Monday I'll have to start giving 2 lectures again. On Monday, Wednesday. Okay. So, we'll be proving today and presumably also Monday several propositions. So let's suppose that I have 2 solutions. I call them U lambda and B lambda, are solutions of the ODE from a previous board. So we have E equals lambda R B. So they both satisfy this ODE. They do not necessarily satisfy the boundary conditions, so I'm not making any assumption about that. All we know is that there's solutions of this ODE, and I'm going to assume that these 2 solutions are linearly dependent. And the reason for that is, that means that U lambda and B lambda describe all possible solutions of this ODE for this fixed value of lambda. So keep in mind, in this whole discussion, lambda is some fixed value. Okay. All right. So given these 2 solutions, then lambda is an eigenvalue of a regular Sturm-Liouville problem. So it's focusing on a regular, not periodic. So for a given boundary operator, if and only if the determinant of this matrix, where you evaluate you plug both your solutions into the boundary conditions. So top row is at x equals a, bottom row is x equal b. So if and only if this determinant is 0. Okay. I'll just take a moment to prove this. All right. So because these two solutions are linearly independent, and this is a second order ODE, the general solution of this ODE has this form, I'll call it W, is some constant times u lambda plus another constant times v lambda. So all solutions of the ODE have that form. So now suppose I take this general solution and I want to plug it into the boundary conditions, and I want to get 0. So what I can do is I can say that the boundary conditions at A and B apply to W. Well, the boundary conditions are all linear. So this is the same as saying C times the boundary values at boundary conditions applied to U lambda plus D times the boundary conditions applied to V lambda. That's for x equals A. And the same thing for x equals B. U lambda, V lambda. Okay. Now, I can write that as a matrix vector product. So this matrix has the boundary conditions applied to both solutions. So x equals A at the top, x equals B at the bottom. Okay. Times the vector CD. And I want this to equal 0 in order to have an actual eigenfunction and lambda be an eigenvalue. The eigenfunction has to satisfy the boundary conditions. Now, I will definitely satisfy this system of equations if C and D are both 0, but that's not what I want. I need a non-trivial solution. Eigenfunctions are never allowed to be 0. So this vector must be non-zero. Okay, so we are looking for a non-trivial solution, by virtue of this being non-zero, to a homogeneous system of linear equations where the right-hand side values are all 0. Now, when does a homogeneous system of equations have a non-trivial solution? For anyone who learned that and retained that from linear algebra. Homogeneous system of equations has a non-trivial solution if and only if what? Determinant? No.
Is 0.
0. Yeah, it's non-zero for a non-homogeneous system to have a unique solution. Yeah. So we have a non-trivial solution which would imply an eigenfunction, therefore lambda an eigenvalue, if and only if the determinant of this coefficient matrix, which is just u lambda and v lambda plugged into the boundary conditions, is 0. So once that happens, you know you have a non-trivial solution. You have a non-zero C and D. Well, one of them could be 0, but they both cannot be. And if that happens, W is an eigenfunction, which is true if and only if lambda is an eigenvalue. Okay. So you're able to work out the general solution of the ODE, preferably if lambda is still left as a parameter in your solution. Then you can figure out, okay, which values of lambda give rise to eigenvalues and eigenfunctions. And that's actually what we have been doing in examples. We have some relatively simple sturm-Liouville problems like v double prime plus lambda v equals 0. You solve out your general solution consists of sines and cosines. And then you figure out for the boundary conditions which lambdas give you eigenvalues and eigenfunctions. We didn't do it this way, although you could. But it might be a useful approach for more complicated ODEs. Okay, so any questions about this result? Okay, so at least we have a way of characterizing general solutions of the ODE as eigenvalues or not. And so it all depends on boundary conditions. Different sets of boundary conditions for the same ODE give rise to totally different eigenvalues and eigenfunctions. Okay. Actually, going to step through an example involving the very ODE that I was just talking about. Example, we have v double prime plus lambda v 0, and on the interval 0 to L. Boundary conditions, we have Dirichlet at one end, and Neumann boundary conditions at the other end. All right. Now, we know what the general solution is. So we'll call it, based on my notation for proof, I'm going to call it W. Is constant times cosine squared of lambda x plus another constant sine squared of lambda x. Okay. So, based on this proposition, we could say that lambda is an eigenvalue if and only if determined this matrix that we get from first substituting cosine into the left boundary condition. So we plug in x equals 0. So we get cosine squared of lambda times 0. And then we plug in the other solution, sine, into that boundary condition. So we look at sine squared of lambda times 0. Okay. And then we plug both cosine and sine into the other boundary condition at x equals L. So we're going to get, for cosine, we're going to get minus sine squared of lambda times L times square root of lambda by the chain rule. And then we plug this into the right boundary condition. So we get cosine square root of lambda times L times square root of lambda. Okay, so that's our matrix. But before we compute the determinant, we'll just go ahead and simplify, because we all know what cosine and sine of 0 are, don't we? So we get 1, 0, and then I have minus square root of lambda sine square root of lambda L, and then cosine square root of lambda L square root of lambda. Okay, so now we can go ahead and take the determinant of that. That's going to be this times this minus nothing. So you get square root of lambda cosine square root of lambda L. And we want that to be 0. So then we're looking at, okay, when is cosine equal to 0?
Multiples of pi.
Yeah. Well, which multiples? Not multiples of pi, but
One and a half, 3 halves.
yeah, odd multiples of pi over 2.
On pi over 2.
Yes. Yeah, that was the thing I was looking for. Yeah, over 2 is necessary. So that means that the argument to cosine, square root of lambda L, must be I'm running it this way, which is the same as n minus a half times pi, n equal 1, 2, and so forth. So now we can say that lambda, the eigenvalues are 2n minus 1 over 2l pi squared. For n starting from 1. And it's important to specify which values of n you're talking about, because otherwise you might get duplicate eigenvalues and duplicate eigenfunctions that are not linearly dependent. Questions? All right. So that's one property about characterizing eigenvalues in terms of whatever boundary conditions you have. All right, so now move on to the next property of many. Now, this next property, the textbook refers to it as symmetry. I'm going to give a slightly more proper term for it, self-adjointness. Okay. Now, to set the stage for all the manipulations I'm about to do, I'm going to briefly slip back into linear algebra mode and actually give really important concept of linear algebra that should always be fresh in your mind anyway, just because it comes up so often. Now this is something that would have been picked up in the linear algebra class. So matrix A, so a real n by n matrix is symmetric if A is equal to its own transpose. Aij is equal to Aji. Actually, I'll give a complex a proper complex analog to that. Is Hermitian if A is equal to its Hermitian transpose, which is the same as transpose complex conjugates. So that's how everything generalizes in the complex case. So in other words, a matrix that's complex but symmetric is actually not nearly as interesting. Now, so focusing on the real case, here's another way to characterize symmetry. So suppose I have, okay, actually I'm going to go back to so for general n by n matrix A. And just for simplicity, I'll keep it real. If I look at this expression, U transpose A times V. So this is just a number, because U and V are vectors. Now, I can, and of course I can associate, so it's U, I can also write this way, U dot product with A times V. Okay. Now, A I can write as the transpose of A, and taking the transpose again because the transpose undoes itself. Okay. And then I use a property that the transpose of a product is a product of a transposes in reverse order. So this is the same as saying A transpose U transpose V. So it's A transpose U dot product with V. If A was a complex matrix, I could do the same thing, except instead of a transpose, it would be the Hermitian transpose. So what happens in general, so this property, that I could take this matrix A and move it from multiplying V over to multiplying U. I could basically like put the shoe on the other foot as long as I take the transpose. So in fact, this can be used, if I didn't already have this definition of a transpose, I could use this property to define transpose. So if A is symmetric, that's the same thing as saying, because what I can do here, if everything is real, I can reverse the order of the inner product and write it that way. So if A equals A transpose, if A is symmetric, that means that U transpose AV is the same as V transpose AU. So that's what I'm looking for here as a way to characterize a symmetric matrix. And we have this definition, Aij equals Aji, but we can also say this, that A is symmetric, if this is true, for all vectors UV in Rn, but you can swap U and V. Okay. Now, the reason I'm doing this, and wandering away from differential equations to talk about matrices, is now if we go to more general linear operators for which you don't have necessarily a readily available notion of a matrix. So for instance, linear operators on functions in a Hilbert space, where you have some inner product. So you have some operator L, like a Sturm-Liouville operator, applied to a function G, and then you take the inner product with F. So you can go ahead and move L from G over to F as long as it's not really L, you take what is called the adjoint of L. Okay. So if L is self-adjoint, which is, so in other words, L is equal to its own adjoint, and the terminology that the book uses is it says that L is symmetric. And it makes sense why we would use the terminology, because this is an analog of a matrix being symmetric. So self-adjoint operators are like symmetric matrices. Then you can say that inner product of F of LG is the same as inner product of LF with G, and if you reverse the order of your arguments to your inner product, you can do that. So in other words, you can swap F and G and still have the inner product turn out the same. And this is assuming that everything here is real. I'm just making a disclaimer so that I don't have to take complex conjugates all over the place. Okay. So, what we're going to look at is the symmetry or self-adjointness of a Sturm-Liouville operator. And the way we're going to discover self-adjointness is we're going to check this property right here. But I wanted to put it in this general context of when you have symmetric or self-adjoint linear operators and how that's defined in terms of inner products. So for instance, you can use this to show that if you're dealing with, for instance, 2-by periodic functions, that differentiation is what's called anti-self-adjoint or skew self-adjoint, that differentiation is the negative of its own adjoint. Or second derivative is self-adjoint. It's equal to its own adjoint. All right, and that's done using integration by parts. So I'm actually going to do that exact same thing right here, but with a more general Sturm-Liouville operator. It almost seems like no matter what class I'm teaching, it's like every course I teach contains a linear algebra course within it. I guess I just can't help myself. Okay. But again, as you've probably all heard from me, it's been said that mathematics is the art of reducing all problems to linear algebra. Okay. So let's let L be a regular Sturm-Liouville operator. So we have minus PV prime prime plus QV. Okay. And I'm going to assume that two functions u and v that satisfy the boundary conditions. So we're dealing with regular Sturm-Liouville problems. Okay. So now if I look at this expression, u times LV minus V LU. Now, this is not exactly the same as what I have in the previous board because these are still functions. If I want to take an inner product, that involves an integral. So I will integrate this later, but before I do that, I want to give myself something simple to integrate. So I'm going to take this expression, plug in what L is here, and simplify. So I have U times L of V, which is this. So I have minus, I'll just put it over here, PV prime prime plus QV minus VLU. So that's going to give me a minus, which makes a plus V PU prime prime plus QU. Okay. Now, notice if I were to expand all this, I'm going to have minus QUV over here, and I'm going to have plus QUV over here. So in fact, the Q terms are going to cancel. So that's convenient. So now all I have left is V PU prime prime minus U PV prime prime. All right. Now I'm going to take this whole expression and integrate it from A to B. So we're working on our interval AB for a Sturm-Liouville problem. Okay, so now I'm integrating that. So I have v pu prime prime minus u pv prime prime dx. And what I'm going to do is I'm going to apply integration by parts to each term, each of these terms separately. So for the first one, this is going to be my u, and this is my dv. And similarly, u is u, and this is my dv. Integration by parts, you can think of it, actually carry on a lot more efficiently, think in terms of you're shifting a differentiation operator from one part of your integrand to the rest of your integrand. So I'm going to get u times v, so that's going to give me v pu prime minus u pv prime, because now the part of parentheses here, I'm taking a derivative away.
Are those both DVs right there?
These?
Yeah.
Yes. Just because I'm doing separate integration by parts,
Okay.
but this plays a role of dv in the two cases. And the thing is, and I think about this every time I teach integration by parts, and you're picking your u and dv, your dv should be something that is easy to integrate. Well, what's the easiest thing to integrate? A derivative. Yeah. So this is my, and I know my choice of function letters is unfortunate. U times v,
Yeah, I think that's what was throwing me off.
and here's my other u times v. Okay. And all of this is evaluated at the limits a and b. So this is the uv part of integration by parts. And then I have a minus integral of v du. And what does that do? You take this differentiation and shift it onto the other part. So now you get v prime pu prime minus u prime pv prime. What happens to that integral? What? Yeah, both terms are exactly the same. Everything's written in a different order. So this whole integral is 0. Okay. So now I have, so now I have this, and okay. I'm going to write out what this is. So this is v of b, p of b, u prime of b, minus u of b, p of b, v prime of b. Okay, and then I have minus v of a, p of a, u prime of a, minus u of a.
Plus? Oh, never mind, you put brackets.
Yeah, p of a, v prime of a. Okay, and I'm going to simplify this just a little bit because I can do a little bit of factoring. So this is p of b, vu prime minus u v prime, all evaluated at b over here. And then I have minus p of a times the same expression except evaluated at a. Okay. So now we're going to figure out what that is. Now, I'm going to use the fact now that u and v satisfy all the boundary conditions. So if I write out what that is, so I have alpha u of a plus beta u prime of a is 0. Gamma u of b plus delta u prime of b is 0. Actually, mix u and v together. So okay, I'm gonna write this over here. So I'm gonna put all the x equals a stuff over here, the x equals b stuff over here. So gamma u of b plus delta u prime of b is 0. And then same thing for v. Okay. Because what I can do now is I can linearly combine these equations and these equations. And the way I'm going to do that is I'm going to multiply this equation by v of a, and I'll multiply this equation by u of a. This equation I'm going to multiply by v of b, and this equation by u of b. And once I do that, then I'm going to subtract them. Because if I multiply this by v of a and this by u of a and subtract them, what nice cancellation am I going to get? It's almost like a Gaussian elimination in a way.
The alphas will cancel out.
Yeah, because I can have alpha u of a v of a, and here alpha v of a u of a. So the alpha terms will cancel, and all that's going to be left are the beta terms. So I'm going to have beta, so this minus this is beta, v of a, u prime of a, minus u of a, v prime of a, and I'm combining the right-hand sides too, so all of that's 0. And I also have the same thing over here. So if I literally combine these equations, the gamma terms go away. The delta terms remain, and I have v of b, u prime of b, minus u of b, v prime of b, and that all equals 0.
Betas and deltas are non-zero, right?
That's a good. Probably should have been an assumption about that here, because
If they're non-zero, then those guys are 0.
yes, so that's actually what I'm going for, because
Make the whole integral 0.
yeah, because that's actually the idea. That's well, the thing is, there are also certain special cases. Like if I have Dirichlet conditions on both sides, we can already see these are 0. If we have Neumann conditions on both ends, also this is going to be 0. But so what happens is these expressions are exactly what we have here and there. So we get big old 0. So in fact, okay, let's do a counterpoint here. Suppose beta and delta are suppose they're 0. Then alpha and gamma have to be non-zero, and that would give you like special cases like Dirichlet or Neumann, and you can verify separately. Like so, for instance, if beta is 0, then that means that u of a and u of b have to be 0, and you can go from there.
Right. Then you'll get different conditions.
So you explore all the possibilities, you're still going to get 0.
Okay, if delta were 0, then v of b and v of a.
Okay, if delta is 0, then u of b and v of b are 0.
So eventually you're going to end up getting 0.
Yes. So, no matter how you slice it, it comes up 0. Okay. So, because that whole thing is 0, let's take a closer look at what we were evaluating in the first place. This. So this is saying that the integral of ulv dx is equal to the integral of vlu dx. But these are inner products. So this is saying the inner product of u with lv is the inner product of V with LU. Okay. So based on the definition I gave earlier for self-adjoint operators, we can say that L is self-adjoint. In other words, it's symmetric, using the folks' lingo. Okay. All right. Yeah. I have 10 pages of notes here. I've only got for 2 of them. So. This is actually the pace I want. Any questions? All right. Now, and it's this symmetry that's going to help us establish some other nice properties of Sturm-Liouville operators and their eigenvalues and eigenfunctions. Okay. The next property is that all the eigenvalues are real. Okay, so a proposition I can prove here is all the eigenvalues of a regular or periodic Sturm-Liouville operator, Sturm-Liouville problem are real. Because a general linear operator that has a spectrum, has eigenvalues, even if the operator itself is real valued, you could have real or complex eigenvalues, but not in this case. Okay. I'm only going to consider the regular case. After that, the periodic case is really not worth doing. Okay. So let's suppose that we have an eigenfunction. So LV is equal to lambda RV. And actually, my proof does not have an R. Hopefully that won't present a problem. So V is your eigenfunction. And lambda is your eigenvalue. All right, so my proof in my notes does not have a weight function R. It assumes that R equals 1. I'm going to try it with a general R and hope it all works the same way.
That is the weight function?
Yes. Yeah, that's what the role that R has. Okay. So what I'm going to do is, using symmetry, I'm going to take the inner product of V with L of V. Okay. Now, L of V, however, because it's an eigenfunction, is lambda RV. Now, lambda is a constant. I can pull it out. And in fact, what we get is, this is the same as the inner product of V with itself, using a different inner product, R. So you're taking the integral of V squared, but with, or absolute value of V squared, with weight function R. But that is actually a norm squared. And I'll use the subscript R to indicate this is the norm that we're using. So I'll just write out the definition. So it's absolute value squared times R. That's included in the integral. Okay. On the other hand, if I swap these things, LV, V, well, all that does, when you swap the arguments of an inner product, that just takes a result and takes a complex conjugate. So that's just going to be lambda complex conjugate. Okay. And the norm is going to be real, so I don't have to conjugate that. Okay. However, based on the property we had before, these inner products are equal. By symmetry, or self-adjointness of L. That was just proven. So these two have to be equal. So that's going to mean that lambda equals this complex conjugate,
Which is lambda is zero.
and that only happens when it's a real number. Okay, so nothing to it. So linear algebra counterpart, the eigenvalues of a symmetric or Hermitian matrix are all real numbers. Okay. Any questions about this one? All right. Okay, next, very crucial property, the eigenfunctions. Orthogonality. Now, so proposition. What?
I'll come back.
Okay. That's not weird at all. Okay. All right, so proposition, so we have V1 and V2 are eigenfunctions. Of a regular or periodic, doesn't matter, Sturm-Liouville problem. Okay. So we have LV1 is lambda R1 V1. LV2 is, lambda 1, not R1. Okay. R doesn't have a subscript. Lambda 1 RV1, and then lambda 2 RV2. And we're also going to assume that lambda 1 is not equal to lambda 2. So we have eigenfunctions corresponding to distinct eigenvalues. Then V1 and V2 are orthogonal with respect to this inner product with the wave function R. So in other words, I'm saying that the integral is going to be of V1 conjugate, V2, R is 0. So now I'll prove this. So you made it back in time for a good part. With just for a regular case. Okay. So using these relationships between LV1 and LV2, and the fact that L is symmetric, so that tells me that V1 LV2 is equal to V2 L V1. But now I can fill in what LV1 and LV2 are. So I have V1 lambda, oh, wait a minute. Sorry. I need to write this way. Okay. All right, so I have lambda 1 RV2. Over here I have lambda RV1. Okay. Now,
LV2 is lambda 2 RV2.
Yes.
So for the for the left hand.
Oh, yeah. Okay. All right. Now, I can. This is lambda 1. I just did the over. Now I could pull out a lambda 2, V1 RV2. That's a comma in the middle. And over here I can pull out a lambda 1. Now normally I have to pull out a lambda 1 conjugate, but we already established that the eigenvalues are real. So there's no need to conjugate. And I have RV1 V2, but R is a real weight function. So there's nothing to stop me from moving R over here. So V1, R, V2. So I actually have the exact same inner products. So now what I have is lambda 2, V1, V2 with a weight function R. So I'll just move it R to the subscript is equal to lambda 1, V1, V2 R. But the thing is, lambda 2 and lambda 1 are not equal. So if I write it this way, lambda 2 minus lambda 1, inner product V1, V2 with R weight function has to be 0. So
V1, V2.
using a principle, yeah,
That's 0.
using a principle of zero products
That's
from Math 101.
no, that's what I did.
I started in 99.
Oh, okay, yeah. So
I just thought it last week.
yeah, so we reach all the way down to the bottom of the math barrel. And yeah, one of these must be 0. This is known by assumption to be non-zero. So we have this. So we have orthogonality. And that ends that. Okay. Okay. Let's see. Oh, I have a few examples of orthogonality. And okay, I'll see if I can get as far as like halfway through the notes. Okay. That's right, you guys are giving presentations on Friday, so
Can we come?
can't. I guess if you really want to, but well, Mrs. Howell won't be there to ask so many questions. So
But Dr. Schroeder will be there, right?
yes, he will.
Yes.
Oh no.
was short on that, so I skipped a couple steps. But he made sure that I revisited at that time.
His comment was that I should try to use the top of the board. The board paper.
Well, she was mad. She brought all tools and whatever. That's not even fair.
See? Okay. Okay, a few examples of orthogonality. So you have B double prime plus B0 on 0 to L, and the Dirichlet boundary condition. So V is equal to 0 at the endpoints. So the eigenvalues, so this has been worked out before. So lambda n is n pi over L squared, it's sure enough they're real. And the eigenfunctions, so Vn of x is sine n pi x over L. Okay, this is for n equals 1, 2, and so on. Now, you can verify directly, as we've done at various points in the notes, if you take the inner product of any two of these eigenfunctions. So that'd be integral from 0 to L sine n pi x over L sine m pi x over L, and use product of sum identities, and what you get is 0 if m is not equal to n. So, and it's been proven in the general case here orthogonal, but you can see that in this case by working out the integral. And it's equal to L over 2 when m equals n. So as a result, you have orthonormal
Bounded by 2 over L.
square root. So orthonormal eigenfunctions, yeah, because this inner product of itself is a norm squared. So this orthonormal set, square root of 2 over L sine n pi x over L, and going from 1 to infinity. Right. Okay. Now, okay, due to time, since I have the same ODE but different boundary conditions, I'll just quickly state that. So, if you have Neumann boundary conditions, V prime of 0 and V prime of L are 0, then your eigenvalues are n pi over L squared again, but this time n starts from 0. So you have 0 as an eigenvalue, and your eigenfunctions are cosine n pi x over L. So when n equals 0, you have a constant function, v 0 of x equals 1 is an eigenfunction. So what happens in this case, if you take the inner product, Vn with Vm, so that's the integral of cosine n pi x over L, cosine m pi x over L, you get 0 if n is not equal to n. You have L over 2 again if m equals n but is non-zero. So for instance, like V5 in a product of itself is going to be L over 2. If m and n equals 0, you're just integrating 1. So you get L in that case. So you have to normalize a little differently in order to get orthonormal set. of eigenfunctions. So you have square root of 1 over L, and then you have square root of 2 over L times all the cosines. Going from 1 to infinity. All right. So sometimes it's that special case that gets you. So be careful about that. Check, do you have a 0 eigenvalue? You wouldn't in the first case, or sine n pi x over L, because you plug in n equals 0, and you get 0. And eigenfunctions are required to be non-zero. Okay. I have one more case in the notes, I won't do it here, where same ODE, but you have periodic boundary conditions. And in that case, you have both cosines and sines as eigenfunctions, and they have the same norms and so forth, except actually, briefly over here, a periodic case. V of 0 equals V of L, V prime of 0 equals V prime of L, and you have your eigenfunctions. Un is cosine 2 pi n x over L, n starting from 0, and Vn of x is sine 2 pi n x over L, n starting from 1. Okay, and then the eigenvalues is 2 pi, dang it, 2n pi over L squared, and starting from 0. And so the reason why I want to take a little time to focus on this case anyway is you have multiplicity 2 eigenvalues. For a regular Sturm-Liouville problem, each eigenvalue only has one linearly independent eigenfunction. But for periodic, you can have 2. So when n equals 0, you only have the cosine. So it's 1, a constant function. When n is greater than 0, so for n equals 1, 2, and so forth, you have both the cosine and sine as the eigenfunction. So multiplicity is equal to 1 when n is 0, and 2 for all other values of n. Okay, so that's a stark difference between the regular Sturm-Liouville problem and the periodic one, is that you're allowed to have multiplicity 2 eigenvalues. Okay. Now, last few minutes, last property I'll prove today, is that not only do we have real eigenvalues for these Sturm-Liouville operators, you can also choose your eigenfunctions so that they are real. Okay. Hopefully I can do this in 5 minutes. Okay. All right. Okay, so proposition is lambda is eigenvalue in a regular or periodic case, either one. Then the subspace spanned by the eigenfunctions, however many of them you have that are linearly dependent, has a real orthonormal basis. Now, for first case, actually one thing I quickly want to check. So there's two possibilities here because of possible multiplicities, like I just showed in the example, and that's one reason why I wanted to do it. Okay. All right. So there's two cases. The first is the multiplicity is equal to 1. And suppose your eigenfunction, so you have an eigenfunction, and it has real and imaginary parts. Okay. Now, it can be shown that real and imaginary parts are both solutions of the that also okay. Of the Sturm-Liouville problem. In other words, they satisfy the ODE and they satisfy the boundary conditions. And V itself is not allowed to be 0 because it's an eigenfunction. So that means that either the real part or the imaginary part has to be non-zero also. Not necessarily both. So that means that W or Z is an eigenfunction also. So if you have any eigenfunction, if it happens to be complex, you can break off a piece of it, real or imaginary part, and that will be an eigenfunction. So either way, you can get a real eigenfunction. Now, orthonormal is trivial because you have only one function in the set because of the multiplicity 1. The other possibility is multiplicity 2. So in that case, you have two eigenfunctions from the same eigenvalue that are linearly independent. Okay. All right. And you have the same thing. Then you have V1 is W1 plus I Z1, and V2 equals W2 plus I Z2. And what happens is all four of these functions, W1, W2, Z1, Z2, are all eigenfunctions at least those of them that are non-zero. You have to have at least two of them be non-zero. Otherwise, either V, because keep in mind, V1 and V2 are both non-zero. Okay. So what that means is, from the set, you can find two linearly independent eigenfunctions. Okay, reason why is, suppose you can't. Well, that would mean that all four functions are scalar multiples of one another. But if that were the case, V1 and V2 would not be linearly independent. Because you could show if everything here is a scalar multiple of W1, then V2 is a multiple of V1. Okay. So So let's write this here. So if that's not true, V1, V2 are not linearly independent. Okay, so that's something you can show directly because, all right. So, so now that you have two linearly independent eigenfunctions, the proposition says that you can have a real orthonormal basis, but we only have linearly independent. If you have linearly dependent vectors or functions, how do you make them orthogonal or orthonormal? What's the process that's used to do that? Does anyone remember from linear algebra?
It had a name.
You divide by
Yes.
The norm.
Graham-Schmidt.
Graham-Schmidt or
Yeah. So, so use a Graham-Schmidt orthogonalization on the two linearly independent eigenfunctions that you get from those two real parts and two imaginary parts. And the result of that is an orthonormal basis. Your orthonormal basis is only going to have either one function or two. It has the dimensions going to equal the multiplicity of the eigenvalue. We will not have any other multiplicities besides 1 and 2 because this is a second order ODE. You can't have more than two linearly independent solutions. That also satisfy the boundary conditions. So that's it. So we can have we have real eigenvalues. We can get real eigenfunctions. I have many more properties to prove, but I will handle that on Monday.